So now what we want to talk about today is the fundamental theorem of calculus. And anything that's called the fundamental theorem of, is important because it is the theorem that ties together the entire subject. So we're talking about the theorem that ties together all of calculus. This is the theorem that brings the limit and the derivative and the integral definition all together and makes sense of all three constructs in calculus: the limit, the derivative, and the integral. So it is the most important theorem that we'll cover this semester. In fact, it is arguably one of the most important theorems in Cal 1, Cal 2, and Cal 3, because it provides the foundation for everything that follows. So far we have been computing definite integrals as the area between a curve and the x-axis. But we've had to use geometric formulas like circles, semicircles, triangles, rectangles, trapezoids, etc., in order to compute the area between the curve and the x-axis, which only works, of course, if the area between the curve and the x-axis is in some kind of geometric shape. But what if it's not? What if it's just a generic curve of some kind, that we've got some kind of graph here, and it looks like this, and we're trying to find the area that's between the curve and the x-axis, and it is not a geometric shape. So something like this area right here, that's not a geometric shape, and just far, we have no way of computing that area. So the fundamental theorem of calculus is going to tell us a better way of computing the area between a curve and the x-axis without having to use geometric shapes. So what we're going to start with is the mean value theorem for integrals. Now, we've already studied the mean value theorem, but the mean value theorem for integrals is slightly different. The mean value theorem is the one that says if you have a continuous function, then and it's differentiable over an interval, then there has to be a point C between A and B where the slope of the tangent line is equal to the slope of the secant line. That's the mean value theorem, right? Slope of the tangent line equals slope of the secant line. Now we want to compare that to the mean value theorem for integrals. The mean value theorem for integrals takes on the meaning of the average value. So remember earlier when we were studying section 5.2, we talked about the fact that there could be some kind of average y value. And if everything, to get that to stick down, if every y value had that y value, then the area underneath that curve, which is basically a rectangle, would have precisely the same area as the area between the first curve and the x-axis. And we called that point right there F average. So this was called F average. Now, what does the mean value theorem for integrals have to do with that average height that gives a rectangle of the same area as the area between the curve and the x-axis? When we're looking at this, it first off has some of the same conditions. We need to have a continuous function, and it has to be on a closed interval, starting out like the mean value theorem in general. What it says is that as long as you have a continuous function on a closed interval, then that function will take on the average height value at some point in that closed interval. In other words, somewhere it has to hit that average height. And if we look back up here at our picture, you can see that in fact that does have to happen. It happens twice in the picture that I drew. There are two places in the picture where the y value on the curve is equal to that average height that gives the rectangle with the same amount of area. So that's what the mean value theorem for integrals states the mean value theorem is different. It's related. The mean value theorem says that if you have a continuous function differentiable on the open, then you have some point where the slope of the tangent line equals slope of the secant line. The mean value theorem for integrals guarantees that if the function is continuous over the closed, then there's a point C between A and B where the value at C is that average value. Hence the name mean meaning average. All right. Now, one way that we can think about this is by thinking of it as velocity. Velocity is a continuous function. When you start at 0 and you go up to 30 miles per hour, you have to pass through every single value between 0 and 30. You can't go from 0 to 30 without going through 15.78. That means that if your average value over an interval was 85 miles per hour, then at some point in that interval, you were driving 85 miles per hour. That, of course, is the reason why you get a ticket if you pass between two toll booths in such a way that your average speed is over the speed limit. They can claim that at some point you had to have been driving the average value of your time. So here's the actual statement of the mean value theorem for integrals. Let f of x be a continuous function over a closed interval from A to B. Then there exists at least one point C in A to B such that f of C is equal to the average value. Now remember, the definite integral with limits of integration on the integral symbol, this part back here represents the area under the curve. So when we're looking at this graph, this part right here is the area between the curve and the x-axis. And then the 1 over b minus a, this part right here, is the width of the interval. So basically we have the area divided by the width, which again, since we know that there has to be some average value with a rectangle of the same height, this gives us area divided by width, which gives us the height of that rectangle, f average. And this simply says that at some point the function does have to take on that average value. Notice that it is not really requiring that it be differentiable here. The only requirement is continuity. That's different from the regular mean value theorem. Let's go through the proof rather briefly. It starts and says, since the function f is a continuous function on a closed bounded interval, in other words, bounded means it doesn't go to infinity on either end. It goes from A to B. So since it's on a closed bounded interval, then we can apply the extreme value theorem. Remember, the extreme value theorem says that it does have to take on an absolute maximum value and an absolute minimum value on that closed interval. It can either be at a critical point or it can be at one of the end points. And this was the first problem off the last exam. On a closed bounded interval, you are guaranteed that it takes on some maximum value, which we'll call uppercase M, and that it takes on some minimum y value, which we'll call lowercase m. So for all the function values in that interval, they have to be between lowercase m and uppercase m, because lowercase m is the absolute minimum on the interval from A to B. And again, it could be occurring at a critical point between A and B, or at A or at B. And uppercase M is the absolute maximum on the closed interval from A to B. Now, by comparing this, this means that we have to have some M less than equal to this average value less than equal to M, right? By comparison, right? Now, since this value of 1 over b minus a, the integral from a to b of f of x dx, is a number between the absolute minimum and the absolute maximum, and since the function is continuous and it takes on all the values between lowercase m and uppercase m, then we can apply the intermediate value theorem. Now remember, the intermediate value theorem says that it must take on all values between the low and the high, which means that if lowercase m is the low and uppercase m is the high, and f average is a value that's between lowercase m and uppercase m, then there has to be a c between a and b that takes on that value. So again, we have now shown that there has to be some value c between a and b that is the average value of that function over the interval, right? Now, we don't use the mean value theorem for integrals much in and of itself, but it is used to prove the fundamental theorem of calculus. So that's why we did this one. We will work a couple of quick examples. So now we're looking at example 1. We want to find the average value of the function x over 2 on the interval from closed 0 to closed 6. We're going to use geometric shapes, since we have no other method yet, for the area under the curve. Then we're going to go find the x value c, such that f of c is that average height of the rectangle that has the same area as the green shaded area that we see here. So what we're trying to do first off is we're trying to find the area under the curve. Remember, the area under the curve can be written, oops, somehow that came out in 2 colors, can be written as the definite integral from 0 to 6 of the function x over 2 with respect to x. This is the definite integral notation, which represents the area between the curve x over 2 and the x-axis from x equals 0 to x equals 6. Now, so far, the only method we have of doing that is finding the area of a geometric shape, in this case, the area of the triangle, which is equal to 1/2 the base times the height. Now, the base of this triangle, if we measure it on this side right here, the base is equal to 6. And if we measure the height, which is right here, we can see that this point on the curve right there is at 6, 3. Because again, the function is x divided by 2. So when x is 6, 6 divided by 2 gives you 3. So the height is 3. This gives us half of 18, which gives us 9 square units of area. Now we want to find that average value. We want to find that average height. So the next thing we have to do to find f average is to take 1 over b minus a, the integral from a to b of f of x dx. We have the integral of f of x dx, it's 9 square units, and b minus a is going to be 6 minus 0, which is 6. This gives us 1 over 6 times 9, which is equal to 3 halves. Okay, so this means that there has to be some value c between 0 and 6 where the y value is 3 halves. So we're looking for a y value of 3 halves. This means f of c is equal to 3 halves, but f of c is also equal to c divided by 2. And c divided by 2 equal to 3 halves means that c is equal to 3. So looking at our graph up here, when we have the x value of 3, the y value is 3 halves. So this is 3, 3/2. And what this means is if we take that height and we draw a rectangle, the rectangle that I'm shading in yellow has the same area under it as the area under the slanted line, the green shaded area. So the yellow shaded area is the same as the green shaded area. And that's what we mean by the average value. Right? Let's take a look at one more. This is going to be based on this integral, which is on a parabola. So unfortunately, because it's a parabola, we don't have a method of computing the area. So they'll have to give us the area because this is not a triangle, it's curved. And so it's not a triangle, we can't use geometric shapes. We will learn a better method in just a few minutes. So this is the definite integral from 0 to 3 of 2x squared minus 1. And they're telling us the area is 15. Now you'll notice that this graph here drops a little below at this point right here as it's headed towards the vertex at 0, -1. And it has a much larger area above. Remember that area below the axis is negative and area above the axis is positive. So the net area is 15. All right. Whenever you compute the integral, you're getting net area. If you want total area, what do you have to do to the function? Does anybody remember? In order to get total area, what would you have to do?
Take the absolute value.
Very good, Hannon, you're correct. We would have to take the absolute value of the function. All right. So now what we want to do is we want to go find that C, where C is the average value. So again, what we are computing is we're looking for F average, which is equal to 1 over B minus A, the width of the interval, times the integral from A to B of f of x dx, which is the area between the curve and the x-axis. Now our interval is from 0 to 3. So B minus A is equal to 3 minus 0, or 3. So we have 1 over 3, and we have the interval or integral from 0 to 3 of 2x squared minus 1 dx, which we know is 15 because they gave it to us. That gives us a value of 5, right? So somewhere there is a value C between 0 and 3 where the y value at that point is 5. So we need to find f of C. F of C is going to be 2c squared minus 1, and 2c squared minus 1 is equal to 5, right? So we took the C, we plugged it into the function, which was the original integrand, and then we set that equal to the average value, which we know to be 5. Solving that, we're going to end up with 2c squared equals 6, which means that c squared equals 3. So c is equal to plus or minus the square root of 3. But we're talking about an interval from 0 to 3. So the negative square root of 3 is not in my interval. So the only one that I want is the positive square root of 3, because it is in the interval from 0 to 3. Now, if you look at the second picture that we have down here, I have marked off this point right here. This is the square root of 3, 5, right? 1.732 is about the square root of 3. And so you can tell that if I were to shade this region right here, I would get a graph with the same amount of area under that rectangle as is in the green and purple shaded regions. So you can tell that there's additional area here compensating for this area here, but remember this purple is also subtracting from this green. So there's the same amount of area in the yellow shaded region, as the net area between the green and the purple. Now we're ready to actually talk about the Fundamental Theorem of Calculus Part 1. There are two parts to the Fundamental Theorem of Calculus. We use Part 2 far more often than we use Part 1, like 99 to 1. However, on occasion, we do need to use Part 1. So I'm not saying it's not important. I'm just saying that we use Part 2 far, far, far more often, right? So this is an extremely powerful theorem, and it's the one that's going to relate together the concept of the limit, the concept of the derivative, and the concept of the integral. So we're going to get all three of those coming together. In Part 1, it starts by stating to let f of x be a continuous function over a closed interval from a to b. Note that this is the same condition that we need to apply the mean value theorem for integrals, the one that says the function has to take on that average height value. So because it's the same condition, we'll be able to apply the mean value theorem for integrals if we need it. We're going to define uppercase f of x to be the integral starting at a constant value a and going to x, the variable of f of t dt. This is a definite integral. So remember that t is a dummy variable, which shows up in the integral and disappears by the end. So t is a dummy variable. The x is the primary variable. And I know it's the primary variable because it also shows up here inside the uppercase function f of x. The a is a constant. And the whole thing, of course, represents a definite integral, which is the limit of a Riemann sum. All right, so this is definitely the limit of a Riemann sum. Everyone remember that the definite integral is the limit as n goes to infinity of the sum from k equal 1 to n of f of x sub k star times delta x. All right, so this definite integral is equal to a Riemann sum. Notice that the lower limit of integration has to be a constant. The upper limit of integration is x. Okay, now, once we have that, it says if I take the derivative of uppercase f, it undoes the indefinite integral and substitutes the upper limit of integration into the integrand formula, which gives me lowercase f of x over the interval from a to b. In other words, when you take the derivative of a definite integral starting at a constant and going to the variable x, which is in the differential of the derivative, then you end up with the function that is in the integrand, lowercase f, with the upper limit of integration plugged in, the x, times the derivative of the upper limit of integration. Now, why not the lower value? Well, because the lower value is a constant, it would give you a constant. And then when you took the derivative of it, you would get 0. So that this eventually becomes just f of x. Now, this will become clearer when we do some examples. But again, some things to emphasize right now is that the lower limit of integration must be a constant, and the upper limit of integration involves the variable x. Note that you are taking the derivative with respect to the same variable that shows up in the upper limit of integration. The dx in the derivative differential matches the variable in the upper limit. When you do that, you get the integrand function with the upper limit plugged in times the derivative of the upper limit. This is the chain rule, basically. Now let's suppose that the upper limit is not simply x, but is instead some expression involving x. So it could be like x squared, negative x, 3x minus 4, whatever it happens to be. So we'll take an example here and we'll work through it. So suppose that we have the integral from 2 to, let's just say 3x minus 4 of some f of t dt. And then we want to find the derivative of uppercase f. Now we know that uppercase f is an antiderivative, and it does look like an antiderivative function instead of the area. It actually does represent the area, except that we don't know what the x value is. If I give you x, it will compute one finite real number, which represents area. So what I'm going to do is take the derivative of both sides of this equation. And so the derivative with respect to x of uppercase f of x is equal to the derivative with respect to x of this definite integral from 2 to 3x minus 4 of f of t dt. And what that's going to do is it's going to take the function in the integrand and it's going to substitute 3x minus 4 inside of it. And then it's going to multiply this by the derivative with respect to x of 3x minus 4. Now the derivative of 3x minus 4 is 3, so that our final answer would be 3 times f of 3x minus 4. Now, you may say, but that's a function. Not really. It's an expression. If I gave you that x was equal to 5, you would be able to compute what this is, and it would give you one finite real value. If I gave you x equal 10, you'd get a different value. And these represent the area under the curve stopping at an arbitrary x. So what we're looking at is a curve like this. We're starting at A, but we're not specifying where x is. So the area under the curve is going to start out here. And let's suppose that the first one goes up to x1. You plug in that x value and it gives you the yellow shaded region. But if you were to change the x value and maybe make it x2, it would give you the area in the purple shaded region, which includes the yellow shaded region. So it's stopping at an arbitrary x value. So it is actually a definite integral without specifying where b is. Let's now look at the proof. The proof is a little bit long and a little bit complicated, not something I'm going to test you on, but something that you need to see because it is the fundamental theorem of calculus. So where does it start and how does it pull together all of these various constructs we have in calculus? The limit, the derivative, and the integral. We're going to start with the definition of the derivative as the limit of a difference quotient. So we're going all the way back to chapter 2. So we have uppercase f prime of x as the limit as h goes to 0 of uppercase f of x plus h minus f of x all divided by h. Hopefully you remember that this is one of the 3 definitions of the derivative. One with h, one with delta x, and the other one f of x minus f of a over x minus a, the limit as x approaches a. Does this ring a bell? I hope so, because you've got a final exam coming up in 2 weeks, all right? In fact, I believe it's 2 weeks from today, isn't that right? Okay, so this is a good review of that. So we're going to use the difference quotient definition. Then we're going to take the difference quotient definition and we're going to factor out the 1 over h. So you can see that the 1 over h is just being factored out. That leaves us with f of x plus h minus f of x. Now we're going to use the definition of what we defined f of x to be. Remember, we defined uppercase f of x to be that definite integral that goes from some constant a up to x plus h, in the case of f of x plus h, of f of t dt. So the upper limit of integration matches what is inside of the function. And the second one will be the definite integral from a to x of f of t dt. So we're substituting using the definition of what uppercase f of x is. Now we're going to use properties of integrals to manipulate these two definite integrals to get them in a slightly different form. So let's scroll down. So here's the original difference quotient. Factor out the 1 over h. Rewrite using the definition of f of x, uppercase. And now we're going to work on manipulating the integrals. So this step right here is the difference quotient. Oops. This is factor out the 1 over h. This is use the definition of uppercase f of x. And now we're going to do something different. Remember that there is a rule for definite integrals that we learned in section 5.2 that says if you reverse the order of the limits of integration, it introduces a negative into the integral. So because it was originally a to x, if I switch those and make it x to a, that changes the negative in front of it to a positive. So I reverse the limits and change the sign. Now the advantage is now I have an integral starting at a and going to x plus h, and then I have one from x to a. So in a sense, if I were to rewrite the order of these two, I have the integral from x to a of f of t dt plus the integral from a to x plus h of f of t dt. In other words, the upper limit of this one matches the lower limit of that one. And there was another property of integrals that says when they match like that, I can slide them together and write them as one combined integral from the first lower limit to the last upper limit, leaving out the part where it goes to a. Remember that a is a constant. So we have now the integral from x to x plus h of f of t dt. Now x to x plus h is a very small amount on our particular graph. This is just the formula, what we have now for the average value. Does everybody see that? Remember that we've got a graph coming out like this. We've got a over here, and we've got some x here, and then some small amount, and we move over to x plus h. And this small amount that we move over right there, that's h. So the difference between x plus h and x is h. That's the width of that interval. So we're talking about well, actually, we're only talking about, if I can get it, the area between those two spots. So we're talking about that area there, starting at x and going to x plus h. The width of the interval is h, so I have 1 over b minus a times the definite integral from x to x plus h, a to b, of f of t dt. This represents the average value. So we have an average value right here up to the limit. So now we're going to be taking the limit of this average value. By the mean value theorem for integrals, there has to be some c in the interval between x and x plus h that does take on this average value. So this is where the mean value theorem for integrals comes in. There has to be some point that has that average height. So looking at our picture over here, there has to be some C right here that's equal to that average height. And C is between X and X plus H. So now we've got that interval. I guess I should have made the interval a little larger so we could see it a little better. So I've got to have some C value where the function value at C is equal to that average value. Now, C has to be between X and X plus H. So as we make H go to 0, C is going to approach X. As H gets smaller and smaller, the distance between X and X plus H gets smaller and smaller and smaller, and they start coming closer and closer together, which makes the value of C, which has to stay in that interval, get closer and closer to X, the one end that doesn't change. As that happens, then C approaches X, so we can say that the limit as H goes to 0 of f of C is the same as the limit as C approaches X of f of C. And because of continuity, that has to be f of X. Therefore, we have proved that the derivative of uppercase f of X is equal to lowercase f of X over the interval from A to B, which is the fundamental theorem of calculus part 1. Now let's see how we actually put this into practice when we're working examples. So let's take a look at example 3. I'll definitely put at least 2 of these on the next exam. They're important. And if you understand how they work, they're also super easy. All right, they should be gimme problems without too much work or thought. So this says use the fundamental theorem of calculus part 1 to find the derivative of g of r as the definite integral from 0 to r of x squared plus f of x dx. Now the x that's in the definite integral is a dummy variable. The true variable is the r because it's inside the function g and it's in the upper limit of integration. So the true variable is r. So what this says is I'm going to take the derivative with respect to r of the definite integral from 0 to r of the square root of x squared plus 4x dx. Now we want to note that the dr here matches the variable there. And since those two match, the derivative and the integral undo each other. They're inverse operations. The derivative and the integral are inverses. So they undo one another and it leaves behind this radical. Now, when I have the radical, I have to plug in the limits of integration. But if I plug in the 0, I get a constant, and the derivative of a constant is 0, so that only the upper limit of integration remains. So this becomes quite simply the square root of r squared plus 4r times the derivative with respect to r of the upper limit of integration. Now the derivative of r with respect to r is of course just 1. So we end up with the square root of r squared plus 4r. In other words, the upper limit of integration gets substituted into the integrand function, and that's the result. There's really no work to do. You can just write the answer down almost immediately. Now let's take a look at another example. This is going to be example 4. And in example 4, both the limits of integration are variables. So I have the derivative with respect to x of the integral from negative x to x of t squared plus t. Now the fundamental theorem of calculus says the lower limit of integration must be a constant and the upper limit of integration must involve the variable that's in the differential of the derivative. but I've got both limits of integration that have the variable in them. We're going to use that property of integrals that says you can break it up at any convenient point. So I could break it at 5 or 4 or 1 or 32, but usually 0 is an obvious place to break things. So 0 provides a good place. So what we're going to do down here is we're going to split the integral at 0. So we're going to take from the lower limit of integration, the original, negative x, and we're going to break it at 0 and go to 0, plus the integral from 0 to x. Remember, we have that rule that says you can break the integral into two integrals by splitting it at any value you want. So we split it at 0. If you'd rather split it at 1, you can. Now, the next thing the fundamental theorem of calculus wants is it wants the lower limit of integration to be a constant and the upper limit of integration to involve the variable in the differential of the derivative. So I need to move the negative x from the lower limit to the upper limit and the 0 from the upper to the lower. By switching the limits of integration, I introduce a negative. So I get a negative right here. And I've switched the limits of integration so that it goes from 0 to negative x. Now, both integrals start at a constant and go to a variable that involves the variable in the differential of the derivative, x. Now I can split this, since this is the derivative of a sum, I can write it as the sum of two derivatives. So the derivative of a sum is equal to the sum of derivatives. So I split it into two derivatives. This now allows me to go ahead and consider applying the fundamental theorem of calculus part 1. The next thing that I did do was I factored out the -1 and pulled it to the front here. So you can see that this negative, which was right here, ended up on the outside here. In the next step, I apply the fundamental theorem of calculus using the chain rule. So my integrand function is t squared plus t. I take the t squared plus t and I'm going to substitute negative x in place of t. That's what that long vertical bar with the negative x means. Then I multiply that by the derivative of the upper limit of integration, which is negative x. Again, for the second, I take the integrand function t squared plus t. I'm going to substitute in place of t the upper limit of integration x, and I multiply that using chain rule by the derivative with respect to x of the upper limit of integration. So now when I substitute in negative x for t squared plus t, I end up finally with this expression down here, which is 2x squared. Now, this is not a family of functions. This is not an indefinite integral. This is not an antiderivative function. This is actually something that represents the area under the curve. If I then told you x is 2, then you would substitute 2, square it to get 4, multiply 2 to get 8, and you would say the area integrating from -2 to 2 under that curve is an area of 2, of t squared plus 2, or t squared plus t rather, right? So it is an expression that gives area under the curve. All right. Now let's take a look at one more. We want to take a look at this one. The example here, note that we have the lower limit of integration involving the variable that is in the differential of the derivative. So we know we're going to have to move that to the upper limit of integration, and the constant 10 has to get moved to the lower one. So the first thing we want to do is reverse the limits. So we switch the order, and that introduces a negative. Then we pull the negative out of the integral and out of the derivative so that we have it at the front. Then we have, notice here, we've got the same variable in the upper limit of integration as we have in the differential of the derivative. So we can apply the fundamental theorem of calculus part 1. We're going to take the inside function, the integral, 1 over t squared plus 1, and we're going to substitute t equals x squared in place of t. Then we multiply by the derivative with respect to x of the upper limit of integration, the one that had the variable in it. Substituting x squared for t squared gives us x squared squared, which is x to the 4th plus 1, and the derivative of x squared is 2x. So our final representation is a negative 2x over x to the 4th plus 1. Okay, let's take a moment and let's work example 6. So I'm going to give you maybe a minute and a half to go ahead and work this one out on your own, and then we'll compare our answers. Okay, let's take a look at it. Notice that we have the derivative with respect to x of a definite integral starting at a constant 1, going to an upper limit of integration of x cubed. The upper limit involves the variable x, which is in the differential of the derivative. So I know I can apply fundamental theorem of calculus part 1. The integrand is cosine of t, and the differential of the integral is dt, t being a dummy variable that will disappear by the end. In order to apply the fundamental theorem of calculus, I don't change the integrand because I am undoing the integral. So think of it as the integral finds the antiderivative, and then the derivative takes the derivative of the antiderivative and gets you back to the beginning again, back to what you originally had, which is the cosine of t. So I have the cosine of t, and I'm replacing t with x cubed. Then I have to use the chain rule to multiply by the derivative with respect to x of the upper limit of integration x cubed. This gives me cosine of x cubed multiplied by the derivative of x cubed, which is 3x squared. And I would write the 3x squared at the front so that you get 3x squared cosine of x cubed. Remember that the integral itself is like an antiderivative. So taking the derivative of an antiderivative is like adding 5 and subtracting 5. You've done nothing. So it leaves us back with the original integrand function, which was cosine. Now, on a scale of 1 to 10, put in the chat window how difficult you found applying the fundamental theorem of calculus part 1, with 10 being super hard and 1 being super easy. How difficult was it? Okay, so somewhere between a 4 or 5, lots of people are 5, some 3, some 2s. No one's giving me a 10. Well, you'll be happy to know that of the 2 parts of the fundamental theorem of calculus, part 1 is by far the more difficult. So the next part, which is part 2, is much easier. Let's take a look now at the fundamental theorem of calculus part 2, which is called the evaluation theorem. This is probably the most important part of the theorem in all of calculus. It's the one that lets us relate the indefinite integral without limits of integration to the definite integral with limits of integration. It also is the one that gives us a way to calculate the definite integral without using geometric shapes like semicircles, triangles, trapezoids, rectangles. So we're going to connect the indefinite integral and the definite integral, and we're going to find a way to compute the area between any curve and the x-axis, even if it isn't a geometric shape that is in that area. This is the one that had such a profound effect on the world. This is the theorem, or the part of the theorem that changed everything. All right, so this is the theorem that you can hold responsible for us no longer traveling in carts and on horses. This is the one that led to the Industrial Revolution. So here it is in a nutshell. It says, if I have a continuous function over a closed interval from A to B, so I can draw the graph without picking up the pen. So no jumps, no holes, no displaced points, jumps, holes, displaced points, and no vertical asymptotes. Then let f of x be any antiderivative of the function lowercase f of x. Then the integral, definite integral from a to b of f of x dx is equal to f of b minus f of a. Very simple formula. This is the most important one in all of calculus. You will be using this constantly. You will know this extremely well because you'll be using it constantly. Now it says any antiderivative. Now remember, when we get an antiderivative function from an indefinite integral, we only get it up to a constant plus c, right? So when we get this f of x, uppercase f of x, we usually get something in the form of f of x plus c. And this is the indefinite integral of f of x dx. It says I can choose any of them that I want to compute the definite integral by taking the upper limit of integration and plugging it into the antiderivative function, taking the lower limit of integration and plugging it into the antiderivative function, and subtracting the two. And it's always the upper limit minus the lower limit. If I can choose any of the antiderivative functions, which are good up to a constant, what is the easiest constant to choose? If I can choose any of them, yeah, Caleb is right. The easiest one to choose is the one where the constant is 0. It gives us one less term to worry about. So our typical habit will be to choose that particular one. Now, sometimes we use the notation that you see right here with the vertical bar and a to b on the vertical bar to represent plugging in the values of the limits of integration, so that f of b minus f of a is equal to f of x with between a and b. And that means substitute in those values, upper minus lower, right? So now let's go ahead and look at the proof. Again, it is the most important theorem in all of calculus. And so we need to at least look at the proof and see how it's done. This is just giving you an idea of different techniques that can be used. So we start with what our left-hand side was, which our right-hand side, which was f of b minus f of a. Remember that we are trying to prove that the definite integral from a to b of f of x dx is equal to any antiderivative evaluated at the upper limit minus the same antiderivative evaluated at the lower limit. So we're going to take the right-hand side, f of b minus f of a, and we're going to rewrite it in terms of a sum. Now remember that we're talking about some function, and we've got area. Here's a, and here's b. A is equal to x sub 0, and b is equal to x sub n. And we're dividing this region up into partitions. Remember how we did the Riemann sums? So we have an x1, an x2, an x3, and so on. So we're dividing this region between A and B into partitions. We're going to then have the values of the interim ones added in. So we do what we call add 0 multiple times. So everyone see here where it says add 0, I've subtracted f of x in minus 1 and I've added it. Because I subtracted it and added it, I've essentially added 0. So this is equal to 0. Then I subtracted f of x in minus 2 and I added f of x in minus 2. But again, this is effectively 0. I subtracted f of x1 and I added f of x1, but that's effectively 0. So I've added 0 n minus 1 times. Now I'm going to rearrange the grouping that I have here of the sums and the differences. So I'm going to rearrange so that the first two are together and the second two are together. And then the third two will be together. And then coming over here, this one will go with this one. And this one will belong with part of what's in the dot, 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 right? So when you look at this third line down, this is simply the thing rearranged. And notice that now I have all pluses in between. This is basically the function of the antiderivative at the right endpoint minus the antiderivative at the left endpoint on each partition. So the antiderivative at the right endpoint minus the antiderivative at the left endpoint of each of the tiny little partitions all the way across. We can write this as a sum from k equal 1 to n of f of x sub k, the right endpoint, minus f of x sub k minus 1, the left endpoint. Now we know that f of x is an antiderivative, so we can use the mean value theorem, not the mean value theorem for integrals, the actual mean value theorem, the one that says somewhere the slope of the tangent line is equal to the slope of the secant line. All right, so this is the regular mean value theorem, and we can apply it, and it says that somewhere the slope of the tangent line has to be equal to the slope of the secant line, and we're applying this on one little partition. So we're actually taking f of x sub k minus f of x sub k minus 1, and we're dividing this by x sub k minus x sub k minus 1, and this has to be equal to the slope of the tangent line at that point. And then we move, of course, the x sub k minus x sub k minus 1, and I lost my x over here, to the other side. And I should have this backwards. I can see I've got a typo in here. This should be x sub k minus 1 minus x sub k minus 1. X sub k minus x sub k minus 1, like that. All right. So I'll have to fix my typo. All right. Now what they did was they moved the denominator to the other side by multiplying. And that says that there's some point where the derivative multiplied by the width of the interval has to be equal to, well, now we've got the integral function f of c sub k delta x, all right? That somewhere there is a c that has that property. So f of c sub k is equal to delta x. Delta x is the length of every partition, which is x sub k minus x sub k minus 1. That gives us delta x. Now we're going to substitute the right-hand side that we originally started with, f of b minus f of a, and we worked through what was on the other side. We're going to substitute that out for what we see above. Basically, we took and we added 0 multiple times and minus 1 times. Then we regrouped them so that we had basically the numerator of the slope of the secant line in brackets for each one of these. And then we wrote it as a sum. And then we said that this has to be equal to f of c sub k delta x. So we have the sum from k equal 1 to n of the integral function f of c sub k delta x. This is coming from the mean value theorem. Now we take the limit of both sides as n goes to infinity. The limit of f of b minus f of a is still f of b minus f of a because it doesn't depend on n. So it's a constant. So it just stays f of b minus f of a. When we take the limit of the Riemann sum, we're taking the limit, well, not Riemann sum, but limit of the sum. We get the same limit of f of c sub k delta x coming out of the mean value theorem. But this is a Riemann sum. This is not a Riemann sum, but this is a Riemann sum. This is the function at some special point inside the interval x sub k minus 1 to x sub k, and it's multiplied by the partition. This is the very definition of a Riemann sum. And because it is a Riemann sum, the definition of the definite integral is the limit of the Riemann sum. And so we're able to write this as the integral from a to b of f of x dx, which means, finally, punchline, that the integral from a to b of f of x dx is any antiderivative function, uppercase f, evaluated at the upper limit, minus the same antiderivative function evaluated at the lower limit. And that's the end of the proof. Now, what we want to do is work through some examples, and you're going to find that on a scale of 1 to 10, these are generally, well, 2s and 3s, depending on the method of integration. What makes it difficult is not the fundamental theorem of calculus. What makes it difficult is what's in the integrand, the function in the integrand. But today we're starting with very simple ones. We only have a few rules to evaluate antiderivatives. We have the power rule. We have the integral of e to the x is e to the x. We have the integral of 1 over x is natural log of the absolute value of x. We have the integral of sine is negative cosine, and the integral of cosine is sine. We have the integral of secant squared is tangent, and a few others. But basically, we have very limited options. We will be learning a far more advanced technique called U substitution in section 5.5, which will greatly expand the number of integrals we can evaluate. But for now, we're looking at those rules and those rules only. So we have the integral from 1 to 2 of x to the negative 4 dx. How do you actually apply the fundamental theorem of calculus part 2? What you want to do is you want to start as if it were an indefinite integral and find the antiderivative function. So we're going to apply the power rule like we normally would by adding 1 to the power and dividing by the new power. Instead of a plus c, though, we're going to take c to be 0 so that it's less work, and we're going to substitute in the limits of integration. So we're going to evaluate this antiderivative function between 1 and 2. The next thing I'm going to do is rewrite it in a slightly more useful form, negative 1x to the negative 3 between 1 and 2, which I'm now going to write as negative 1 over 3x cubed between 1 and 2. Does everybody agree that these are equivalent? Okay. Next thing I want to do is I want to substitute in the value of 2 for x. So I have negative 1 over 3 times 2 cubed minus, this is part of the fundamental theorem of calculus, negative 1 over 3 times 1 cubed. This gives me negative 1 over 3 times 8 is 24. So I have negative 1 over 24. A double negative makes it plus. 1 cubed is 1, so I get 1/3. Now writing 1/3 in terms of 24ths becomes 8 24ths. So I get negative 1 over 24 plus 8 over 24, which gives me 7 over 24. Right? Are there any questions about that one? Now, I do want to show one other thing that you can do that can make this a little bit easier to compute. And this is something that I use all the time. Notice up here in this substitution format, the negative 1/3 is actually a constant. I can pull the negative 1/3 out. And I can instead think of it as negative 1/3 times 1 over x cubed between 1 and 2. Then I can leave the negative 1/3 on the outside, and I can simply plug in into the original. And this would give me 1 over 2 cubed minus 1 over 1 cubed, which is a negative 1/3 times 1/8 minus 1. Now, 1 can be written as 8 over 8, so that gives me 7 over 8. So I get negative 1/3 times negative 7 over 8, and that would give me the positive 7 over 24. So depending on what your constant is, sometimes it's easier to pull the constant out and leave the constant as a factor on the outside of the brackets and do the substitution on the simpler part that just involves the variable. Let's apply it again. Let's take a look at this one, which is to use the Fundamental Theorem of Calculus Part 2 to evaluate the integral from 0 to 1 of x minus the square root of x. Now again, we don't have many techniques. Primarily the trig integrals, the integral of e to the x, the integral of 1 over x is natural log of absolute value of x, and the power rule. So pretty much we're looking at the power rule on this one. So we're going to rewrite our integral so that we can apply the power rule. So this becomes x to the first minus x to the 1/2 dx. Now, just as we can split up an indefinite integral, we can split up a definite integral and apply it on each term. My next question is, can I split it across multiplication or division? Yes or no? Michael is shaking his head. Caleb is more definite. Juan agrees. Definitely not. You may never, everyone repeat after me. I may never split an integral across a product. Say it. I don't hear you. I may never split an integral across a product.
I may never split a what integral or a product.
Excellent.
Great.
If I don't make you say it, I guarantee you someone's going to try it on an exam and it will be wrong. Okay, now that I have this, we're going to apply and find the antiderivative function using the power rule. So we add 1 to the power, divide by the new power, and evaluate between 0 and 1. Then we can do the same thing here. X to the 1/2, add 1, which is 2/2, which becomes 3/2, divide by the new power, which is 3/2, and evaluate between 0 and 1. Now you have a choice. You can do it term by term, or you could plug a 1 into both terms and then subtract plugging in 0 to both terms. They're both correct. They're both accurate. They both work in all cases. So let me show you the 2 different ways of splitting this up. So I'll do one in black. One is to do them separately. This is 1/2 x squared between 0 and 1 minus 2/3 x to the 3/2 between 0 and 1. One method is to say 1/2 times 1 squared minus 0 squared, plugging in both limits of integration into the first term. Then I can do the second term, leaving the 2/3 out as a factor, 1 to the 3/2 minus 0 to the 3/2. Again, plugging in both limits of integration into the second term. The rest of it is simply algebra and arithmetic. 1 to any finite power is 1. So this gives me 1/2 minus 2/3, which I need to write them both as sixths. So this becomes 3/6 minus 4/6, which is a negative 1/6. That's one method. What's the other method? The other method instead plugs in the 1 to both terms and then subtracts, plugging in the 0 to both terms. So the second one does this instead. 1/2 x squared minus 2/3 x to the 3/2, all evaluated between 0 and 1. So it's going to take and it's going to plug 1/2 times 1 squared minus 2/3 times 1 to the 3/2 minus, and now you have to open up a bracket in order to be sure that you don't mess up the signs, since you want to subtract both of them at the lower limit. And then you do it again with the lower limit plugged in place of the variable. So 1/2 times 0 squared minus 2/3 times 0 to the 3/2. These both go to 0. And you end up with exactly the same thing you got in the first method. Now, I will admit to you that I use both methods. It just sort of depends on the mood I'm in, what I see first, or how easy I think it's going to be to do one or the other. It works both ways, so I use both methods. Now, what is it that we're actually finding? Let's take a look at this link that's here and remind you of what it is that we're actually getting. The actual function is x minus the square root of x, which you can see here in blue. All right, so it starts out almost like a hook near the origin, goes below the x-axis and then comes up above the x-axis. We're finding the integral from 0 to 1 of that particular region. So we're trying to find the area from 0 to 1, which gives us this function value. So now what we're looking at is we're finding the amount of area between the curve and the x-axis, which is here in this purple region. Now, the reason why this is shaded in green is I wanted to let you see what 1 square unit looks like. That green is 1 square unit. And you can tell the purple is much smaller. So -1/6 of a square unit does make sense. It's about 1/6 of the green space. Let's work another example. This one has trig in it. So we're taking the integral from -π/4 to 7π/4 of sine of x plus cosine of x. Now you can split it into two integrals, but you do not have to split it. You can leave them together and integrate each piece. So I can take the integral from -π/4 to 7π/4. And remember to leave lots of space. This takes up at least 3 lines, if not 4. And then the integrand is sine of x plus cosine of x. And the differential is dx. The x is a dummy variable because this is a definite integral, so we're going to get a number for the answer. I could use any symbol I wanted. I could rewrite this as the integral from -π/4 to 7π/4 of sine of star plus cosine of star d star. In fact, let's do it. It's a dummy variable, so it'll disappear. I need the antiderivative function for sine of star plus cosine of star. Remember, you're undoing the derivative. So the derivative of something gave you sine. The derivative of something gave me sine. Well, the derivative of cosine is negative sine. So to get positive sine, I should have a negative cosine. So I have negative cosine of star. And then I've got cosine of star. I took the derivative of something and I got cosine. Well, it had to be sine. So the antiderivative of cosine is sine. And then I'm going to evaluate between -π/4 and 7π/4. So now we're going to plug in and see what we get. And in this case, I'm going to use method 2 from up above. You can use either method 1 or method 2. I'm going to substitute 7 pi over 4 into both first, and then I'm going to subtract the result when I plug in negative pi over 4. Make sure you put brackets if you use this method around the entire second term. So this becomes negative the cosine of negative pi over 4 plus the sine of negative pi over 4. Now you may need to remind yourself, where's negative pi over 4 again? Oh yeah, it's here in quadrant 4. Where's 7 pi over 4? 7 pi over 4, 4 to get to here, 5, 6, 7. Hang on, that's the same angle, but proceeding in a counterclockwise orientation rather than a clockwise orientation. So when I look at these, the cosine of 7 pi over 4 is 1 over the square root of 2, right? Or square root of 2 over 2, however you want to put that in. It's negative, so this is going to give me negative 1 over the square root of 2. The sine of 7 pi over 4, because it's in quadrant 4, is going to be negative because sine is negative in quadrant 4. So that gives me minus 1 over the square root of 2 again. Then I have a minus with big brackets. Now the cosine of negative pi over 4 is the same location. So it's 1 over the square root of 2, but it's got a negative on it. So this gives me negative 1 over the square root of 2. And then the sine of negative pi over 4, again, is also in quadrant 4. Sine is negative in quadrant 4, so I get a negative 1 over the square root of 2. And what is my final answer going to be? I have negative 2 over the square root of 2 minus a negative 2 over the square root of 2. What's happening? Somebody interpret that
0.
result. Yeah, why? What does that mean? Did we mess up? Let's take a look at the graph using the link that you see right here. And look at the graph, sine x plus cosine x, graph between negative pi over 4 and 7 pi over 4. What do you notice about the area between the curve and the x-axis? It's the same amount above the x-axis as you have below the x-axis. Remember that area that's above the axis is considered positive, and area that's below the axis is considered negative. And if they're the same amount of area, what should you get when you integrate over that region? You should get 0. The net area is 0. You have the same amount of area above the axis as you have below the axis. The net area is 0. What questions do you have about that particular problem? None? Okay, I see some puzzling looks. Let's go on and look at a different one, this one involving e to the x. And you'll see that we have a link to take us to the graph as well so that we can interpret the result. When we're doing this one, we have a definite integral from 0 to the natural log of 8 of e to the x dx. So we want to evaluate the definite integral from 0 to natural log of 8 of e to the x dx. That should take up at least 3, if not 4 lines. Remember that the integral symbol goes below, the hook is below on the line below, and the upper hook is on the line above, and the e to the x dx sits on the line in the middle. So it's actually in the center of the integral symbol, not at the bottom. So the antiderivative function for e to the x is e to the x. This is how we're tying the indefinite integral into the definite integral. We take any antiderivative function. I could take e to the x plus 1, but the easiest one to take is e to the x plus 0. So I choose the constant to be 0, and then I need to evaluate it at the limits of integration. That's the fundamental theorem of calculus part 2. And that's what ties the indefinite integral to the definite integral. You use the indefinite or antiderivative function from the indefinite integral, and then you plug in the limits of integration from the fundamental theorem of calculus part 2, which evaluates the definite integral. This then gives us e to the natural log of 8 minus e to the 0. Remember that you have a college algebra property that says when e and natural log are back to back and touching one another, they're inverse operations, so they undo each other. So this simply leads to 8. E to the 0 is 1. So we get 8 minus 1, which is 7. What we're talking about is 7 square units of area between the curve and the x-axis from x equals 0 up to x equal the natural log of 8. Let's now look at this graph by clicking on the link. And now we can see the graph here of e to the x. Remember, e to the x is a basic exponential. It approaches the x-axis going off towards negative infinity, and it grows very rapidly as it goes up. It generally passes through 0, 1, unless it's been shifted up, down, left, or right. And now we're looking at the integral between 0 and the natural log of 8. Now, the natural log of 8, of course, is this line right here. It's slightly past 2. It's very close to 2, but it's not 2. It's slightly past. See if I can blow it up a little bit so you can see it. Now you can see definitely that it is past the 2. All right. And it's shading that region under there. Now, if we're looking at this region right here, and you want to know how much of that is actually 1 square unit, find 0 to 1 on the y-axis and 0 to 1 on the x-axis. That's 1 square unit right there. So if I were to take a picture of this, if I can find my snipping tool. And we were to substitute the picture back onto our sheet. Let's blow it up a little bit, make it a little larger. All right, so I can get the whole thing on there pretty much. 1 square unit goes from 0 to 1 on the x and 0 to 1 on the y. That's 1 square unit right there. So this forms another square unit. So that's 2. This is 3. This is almost 4, but it's missing a little corner right there where it's kind of curved. So that's 4. And then the rest of what's here has got to make up the other 3, because it is exactly 7 square units, like 7 of those squares, right? That's the meaning of the area. One last part to the fundamental theorem of calculus is taking another look at the average value. When we looked at the average value in section 5.2, we said that the average value is equal to 1 divided by the width of the interval, b minus a, times the definite integral from a to b of f of x dx. In other words, the width of the interval, 1 over b minus a, is multiplied by the area. So area divided by the width gives you the height of the rectangle with the same area. Now we have a new method of computing the area between the curve and the x-axis. We no longer have to use a geometric formula. This will allow us to find the average height of functions that don't lend themselves to geometric formulas. Let's take a look at one like that. We want to find the average value of the cosine of x between negative pi over 2 and pi over 2. So remember what cosine of x looks like. It starts up here at 1 and then it comes down and curves like that. And so we're basically looking at the value in between here and here. Remember that the cosine of pi over 2 and cosine of negative pi over 2 is 0. So we're looking for an average value or a height that has the same amount of area under that rectangle as is under this part of the curve, the central bump. So what we're going to do instead is we're going to find f average by computing 1 over b minus a times the integral from negative pi over 2 to pi over 2 of cosine of x dx. The x is arbitrary. We could use any variable we wanted. We could use star, we could use a happy face. It's a dummy variable in a definite integral. So this is going to give me 1 over pi over 2 minus negative pi over 2. And what is the antiderivative function of cosine? I took the derivative of something and got cosine. So to undo it, I get backwards to the original, which was sine. So this is going to be multiplied by sine of x, which has to be evaluated between negative pi over 2 and pi over 2. Pi over 2 minus a negative pi over 2 gives me 2 pi over 2, or pi. So this becomes 1 over pi times the sign between negative pi over 2 and pi over 2. I'm going to leave the 1 over pi out, and I'm going to plug in the upper limit of integration first, and then subtract when I plug in the lower limit of integration. Now remember that sine is the y value, and pi over 2 is up here, and negative pi over 2 is down here. And the y value in those locations are 1 and negative 1 respectively. So that gives me 1 over pi times the integral of, or not integral, times the quantity 1 minus a negative 1. That gives me a double negative, which makes it 2 over pi. Now, 2 over pi turns out to be about, let's see, 2 divided by pi is about 0.637 square units of area. So it's not even 1 full square unit of area between the cosine and that. Now this is actually, I take that back. That's not square units. What is that? That's f average, all right? So we have the average value there, all right? I forgot what we were looking for when I was doing it. We're looking for f average. So when we're looking for f average, we get 2 over pi as the height. Let's take a look at the link and see what it is. All right, so here is our graph. I don't know why that's there in the middle. So now we've got the curve cosine of x. I've shaded the region between negative pi over 2 and pi over 2, kind of a blackish gray. And then I found the height 2 over pi, and I shaded the region between negative pi over 2 and pi over 2 up to a height of 2 over pi in green. So what does this mean? The area in green is exactly equal to the area in the dark gray. So the average value gives the height of the rectangle that has the same area under it as the original curve. Okay, we have one more to work. which is number 12. It says use the fundamental theorem of calculus part 2 to find the average value of the function e to the x over the closed interval from 0 to 2. So again, we're looking for the average value. So we're going to take 1 over the width of the interval. B minus a is 2 minus 0. The integral from 0 to 2 of e to the x dx. Now, we don't have to use x. We could have used t or something else. It's a dummy variable. It's going to disappear when we plug in the upper and lower limits of integration. This gives me 1 over 2. The antiderivative function of e to the x is e to the x, and I'm going to substitute in between 0 and 2. I'm going to leave the 1/2 outside, and I'm simply going to plug into the e to the x antiderivative function, e to the 2 minus e to the 0. Don't make the mistake of thinking e to the 0 is 0. It's not, it's 1. So this gives me 1/2 times e squared minus 1. Now you could multiply it out, but you certainly don't have to. This is approximately equal to 3.2, which is the height of the rectangle, which has the same area as is under the curve e to the x between 0 and 2. Let's take a look at the function and see what it looks like. All right. Here you can see that we've got the curve e to the x plotted in that orange-red color coming up like this. Then we have the area between the curve e to the x and the x-axis shaded in this sort of dark gray black color that you see right here. Then we found the height, which corresponded to 1/2 the quantity e squared minus 1. And we drew a rectangle with that height going between 0 and 2. The area that is shaded green in this rectangle with the average height of 1/2 quantity e squared minus 1 has the same area as is under this gray shaded region. So this is the end of the fundamental theorem of calculus. It was a complete game changer for the world. It changed everything after this was realized. Things just exploded and began developing more and more and more, and they were able to solve more and more scientific and engineering problems. Next time, we're going to be taking a look at what's called the net change theorem, which on a scale of 1 to 10 is not nearly as important as the fundamental theorem of calculus. But then we're also going to take a look at what's called U substitution. On a scale of 1 to 10, U substitution is a 10, right up there with the fundamental theorem of calculus, or just below it.